So, hi, I'm Professor Geraint Jones. I'm head of the Planetary Science Group here at UCL's Malad Space Science Laboratory, and I'm also the lead proposer of Comet Interceptor, a mission that's been recently selected by the European Space Agency to hopefully launch in 2028.
Thanks very much for speaking to us today, Geraint. Because I know you're obviously very busy because as we're speaking, you're kind of right in the midst of the mission being accepted and all the organisation, aren't you?
Yeah, that's right. So the timeline was we submitted a proposal, a first stage proposal to ESA back in October 2018. And then we found out at the end of November we were in the final six. So we understood that 23 proposals had gone in. And then we had to submit a second stage longer proposal in late March. And then we were invited to interview at ESTEC, one of the ESA centres in the Netherlands, in early May. And then on June the 19th, we got the fantastic news that we'd been selected by ESA. So yeah, that proposal I'd co-led with Colin Snodgrass at the University of Edinburgh, but we have got a huge international team, about 130 of us on there. But yeah, we went straight into studying the mission in more detail with ESA. So clearly they, from looking at the proposal, they'd judged it to be scientifically valuable, definitely worth doing. And based on what we'd proposed, they believed it was definitely doable. But now, over the past few weeks, we've been having what's called a concurrent design facility study. So this is where lots of engineers at ESTEC, the ESA Centre, get together several times a week and work intensively on analysing the nature of the spacecraft and the mission and the instruments that will be flying on it.
Fantastic. So, what exactly is the mission going to involve? I mean, Comet Interceptor kind of gives it away, but it wasn't
It does a bit,
yeah.
yeah. Yeah, so it basically does what it says on the tin or whatever the spacecraft will eventually be made of. Um, so all previous Comet missions that were targeted to go to comets anyway went to comets that have been around the sun many times before. So most famous of which being Comet Halley, of course. So people knew centuries beforehand that it was going to come past the sun in 1986. So there was plenty of lead time for several space agencies actually to prepare missions to go to that comet. And all the other comet missions, dedicated comet missions at least, have been to comets like Churyumov-Gerasimenko, where Rosetta went, which is a short period comet. So we know where it's going to be at any point in time, at least to the accuracy we need to send spacecraft there. So these missions have taught us a huge amount. So there was a huge breakthrough in the 1980s from Halley and one other comet that was encountered then. And then NASA had several missions such as Stardust and Deep Impact that looked at other comets after that. And then, of course, most recently we had Rosetta from the European Space Agency, which spent a couple of years traveling alongside a comet, dropping a lander down onto its surface and telling us more about what these mysterious bodies are made of and what makes them tick. But the type of comet we haven't encountered yet with the spacecraft is one that's coming in towards the sun for the first time. So we really would like to see one of these close up and study them in great detail because, as many of the viewers will know, comets are believed to be the leftovers of when the planets formed. So they're as old as the solar system, and millions upon millions of them were scattered out of the solar system around the time that the planets were being formed into a deep freeze, really far away from the sun. And occasionally, some of them come back in towards the sun. They warm for the first time in billions of years, releasing gas and dust. And we see these spectacular tails occasionally from some of these long period comets. So the problem with encountering one of these comets, of course, is that we don't know when and where they're going to arrive. So the ones that are coming in for the first time, what are called dynamically new comets, they can come basically from any direction in the sky. So we don't know where they'll be coming from, where they're going to cross the plane of the Earth's orbit, how close they are going to get to the sun, etc. So previously, typically you get maybe a year or two's worth of forewarning when a comet's coming in. Comet Hale-Bopp, for example, that was about 2 years' notice. Then more recently, with the advent of ground-based survey telescopes, that distance at which new comets are being found is moving further and further away from the sun. And that means that we get more and more forewarning of when a comet is coming in. And in a couple of years' time, there's a really capable observatory due to go online, working in Chile, LSST, the Large Synoptic Survey Telescope. So that's going to map the entire sky as seen from Chile every few nights. And with that facility, we expect to be able to find comets really far out, giving us a lot of warning when these comets are coming in. So it probably won't increase the number of comets found, but it will mean that we'll be finding them further away from the sun than we normally would have done. So that's great, knowing when new comets are coming in. That helps the mission proposal. But also the nature of the mission is that as ESA issued this call for the mission proposals, it was clear it would be launched with the Ariel Exoplanet Observatory mission in 2028. So Ariel is going to be delivered to a Lagrange point, so one of these stable points in space where the sun and the Earth's gravity cancel out, so they're quite stable. It's the point L2, which is on the other side of the Earth from the sun, about 1.5 million kilometers further away from the sun than we are. So any spacecraft that's launched with Ariel will be delivered to this gravitationally stable spot. And it's actually a perfect place to put a spacecraft waiting for a suitable target to be coming in towards the sun. So this combination of our telescopes getting better, finding comets further away, and this mission opportunity delivering a spacecraft to actually sit in a place which would be ideal to wait for a suitable target is perfect for Comet Interceptor.
So once you actually find a comet that you want to go and study, are we able from the ground to kind of point it towards that, or how does the spacecraft actually know to go towards that particular comet?
So very good question. So the expectation is once potential target comets are found, we'll track them, refine the orbits, find out exactly where their future trajectory is going to take them. Because we're limited in mass, we have to stay close to the Earth's orbital plane, so the plane of the ecliptic. We can't go far north or south of it. So we can only encounter comets when they're crossing that orbital plane. So this limits which comets we could potentially go to. And also with the spacecraft as well, we can't build one that will cope with going really close to the sun or really far away. So it's going to be a range of distances around the Earth's orbit. So we need to define exactly what that range is as well. As part of the preparations for the mission, we'll be setting up a committee basically that's going to look at each potential target comet as it's found. We'll find out what its predicted orbit is, where we would be able to encounter it, how easily can we get there. And because these comets come in from anywhere in the sky, the flyby speed can vary a lot. So if you have a comet going around the sun the same direction as the Earth does, and if it's not highly inclined, so it's close to the orbital plane of the Earth, then the flyby speed might be as low as 10 or 20 kilometers per second, which is ridiculously high for us, but relatively slow. But if you have a comet like Comet Halley, which the Giotto probe encountered in 1986, orbiting the sun in the opposite direction to the Earth, the relative speeds can be very high. So you're talking about 60 or 70 kilometers per second. So we have to design the spacecraft to be able to cope with a wide range of flyby speeds as well. I mean, Giotto did survive that encounter, so we know that it's possible. But we'll have to provide dust shielding and things as well, which add mass to the spacecraft. So we may end up with not being able to go to every single comet we'd like to. There'll probably be a range of different comet orbits that we'll be able to intersect. And that's part of the study that's just started up now, really.
And once it gets to the comet, what sort of science will it be doing, and how is the spacecraft equipped to carry out that science?
Yeah, so one big new thing we're doing is that it's more than one spacecraft as well. So our proposal is for three spacecraft, a primary one, which for now we're calling Spacecraft A. So this will be the one that carries the other two smaller spacecraft to the comet. It'll have the main engine on there, the main power supply. It'll be the spacecraft through which we'll be communicating with the Earth. And we're proposing that that one doesn't go too close to the comet, so it will need some dust shielding, but it won't go to a high risk region. So we're thinking of that flyby distance at the moment of being around 1,000 kilometers, which is pretty close, but not dangerously so for most comets. So as spacecraft A is approaching the comet, it would release two smaller sub-spacecraft, one also provided by the European Space Agency and one by the Japanese Space Agency, JAXA. So these two probes would go closer to the nucleus. So there's a significant risk that we might lose these sub-spacecraft if they're hit by dust at high speed, for example. So they need to be sending back their data in real time to the main spacecraft to save all the data we can. So they're almost expendable, basically. If one or both of them gets destroyed, it's fine. It's part of the mission. We knew that it was a significant risk, and we'd be sending the data back to the main spacecraft for safekeeping to send back to Earth later. So in terms of instruments, so we'd have a main science camera on spacecraft A that would look at the nucleus at very high resolution. We'd also have infrared instruments mapping the comet nucleus as well. So we want to see, does the nucleus look different to Halley, Churyumov, Gerasimenko, and the other comets we've seen so far? Or if it's coming in towards the sun for the first time since it was formed, is it radically different in appearance? What are the ices on the surface? Are there ices that we haven't seen at other comets? And comet nuclei, all the previous ones we've seen close up, are very, very dark because they've got thick layers of carbon-rich dust on their surfaces. This may build up as they go past the sun with every orbit. So maybe we'll see that these more pristine comets have got very little dust on the surface, so maybe it'll be more reflective. We don't know, and the only way of doing is finding out is to go closer. So as well as those visible and infrared cameras, we've also got plasma instruments. So we'll be sensing the magnetic field around the comets, hopefully at all three spacecraft, and how the solar wind is flowing past the comet. We'll also have a mass spectrometer, which will sample the gas that's around the comet. So that will be on one of the sub-spacecraft. And it'll give us detailed compositional information about what exactly the gases coming off the nucleus are made of. And we'll also have cameras on the smaller spacecraft as well, but they're unlikely to be better in image quality than what's on spacecraft A. But by having three viewpoints, even though it's just a fast flyby, we can't go into orbit around this nucleus, we'll get three different viewpoints. So we'll be able to build up a 3D shape model of the nucleus. And on top of that, we also propose a camera that's going to map the entire sky. And doing the scientific reason for doing that is to understand how dust scatters light in the coma around the comet, and that can tell us about the shape of the dust. And look at the polarimetry. So if you put Polaroid sunglasses on, or these 3D glasses you get at a cinema, if you rotate them in daylight, looking at different objects, you'll see that objects look slightly different depending on how they scatter light. So we plan to be making those kinds of observations as well. So with dust instruments as well, measuring how many impacts we have at all the spacecraft. We'll learn about the comet's surface, what's coming off it, and also the 3D structure of the material around the comet as well, so the dust and the gas as well. So we're packing in a huge amount of science into a really small mess. So we are studying the mission with ESA now. So what we've proposed, maybe not everything can fly. So there are mass and power constraints, but we're quite hopeful at the moment that we'll be able to do fantastic science with this mission.
Was a lander ever a possibility?
Unfortunately not, no. So to land, we'd have to slow down. So even if at one of the slower flyby speeds of 10 or 20 kilometers a second, that would mean a lot of fuel. And even if we were to do that, then there'd be a problem with communicating with the lander as well, because the flyby spacecraft would have whizzed past. So unfortunately not. So there's there's a lot to be said to going down onto a nuclear surface, as we saw with Philae. Even though it only operated for a couple of days, we learnt a lot from that. But the nature of this mission, unfortunately, the flyby speeds are going to be way too high. So that's for another mission in a few decades' time, I think.
Even still, though, I mean, with the Rosetta mission, the most remarkable thing from, I think, kind of non-scientist's point of view was just the incredible images that we got of like plumes of bursting through the surface of the comet and things like that. Do you think we can expect that the similar kind of output from this mission, like amazing images and things like that, or is it too far away? Is it going to be more like the New Horizons flyby?
Yeah, well, it's a fair question. So a lot of that will be decided by how active the comet itself is. So if we're very lucky, then we might get something on the scale of Hale-Bopp, which was a huge comet, which those of us who were around in 1997 will remember was spectacular, and you could see it in the sky for weeks on end. Those kinds of spectacular comets are rare, and it's more reasonable to expect something of modest activity level. But even so, where the Rosetta target comet was a fairly low production rate comet, it's not particularly active, and yet we saw these amazing dust jets coming off. So the expectation is that, for pretty much most targets that we see as being possible at the moment, we should be able to see dust jets coming off the surface as well. And we're aiming for as high a resolution at the nucleus as possible with the primary science camera. So we're hoping for image resolution of better than 10 meters at least. So that will definitely give us a sense of what the shape of the surface is like, how it's been changed over time at huge distances from the sun over billions of years.
And this all ultimately pertains to the question of how did the solar system form and how did it evolve over time?
Exactly, yeah. So we have learned a huge amount from previous comet missions, but a pristine comet like this, we haven't seen before, and it's the best time capsule we have, basically, from the early solar system, at least the bits where that were far enough from the sun for ices such as water ice, carbon dioxide, carbon monoxide, etc., to form solids. So it would be extremely valuable to be able to make these measurements.
Well, it's absolutely fascinating, and good luck for the rest of the mission preparations, Geraint. And I just want to say thanks very much for speaking to me today.
It was a great pleasure. Thanks very much for your interest. Thanks.